If you want to study lithium-ion batteries, we need to prepare first the samples. And as lithium-ion batteries contains many chemical species which are very sensitive to moisture and air. So for this we will use the glove box which protects our samples from the exposure to the fresh air.
So this is something what we do. We prepare the specimen, we cut it off out of the battery inside of the glove box. We placed it on the rod, put it inside of the transfer capsule, and we use this capsule to be attached into the electron microscope for further analysis. So what we are doing right now, we are having this sample locked inside of this inert gas atmosphere in the transfer module, and we mounted it on the chamber of the electron microscope, and we use this transfer rod to insert this sample inside of the electron microscope without exposing it to the air. So what you can see here is the scanning electron microscope. It consists scanning electron microscope column, which is used for imaging, specimen chamber, this is where we can place our samples, and it consists also focused ion beam. This focused ion beam is used for milling of the material. So if you want to expose a cross-section or do the 3D analysis, this is what we are using for milling. And we also have TOF-SIMS, secondary ion mass spectrometer, which is used for analysis of lithium inside of the sample, which is essential part for battery analysis.
So what we're looking at here are two data sets, one of a fully discharged cathode and then one of a fully charged cathode. On the left, we have a fully discharged cell. So what that means is all the lithium should be in the cathode. On the right, we have a fully charged cell, and that means theoretically that all of our lithium ions should be in our anode. TOF-SIMS allows us to see that we actually have lithium trapped in our cathode, and we're not fully utilizing our lithium economy in the way that we want to in our battery. This is really useful in post-analysis of batteries because it allows us to link our analysis with our cycling data. So the SEM allows us to look at our samples or our batteries on a microstructure or nanoscale that we wouldn't be able to with just our eyes. These SEM images are very useful to us because they allow us to look at our batteries on a micro or nanoscale. On our left, we see graphite that's damaged from exfoliation, which can happen during cycling. This shows that we're not going to be able to utilize that graphite for lithium because it is too damaged of a material. In the middle, we also have some NMC cathode particles, and as you can see, there's a lot of fractures, a lot of cracks. Lithium, it's harder for it to jump over these cracks, so we wouldn't be able to fully utilize these particles. And then on our very right, we have actual images of the graphene layers that we see in graphite. Now, if this was a charged particle, we might actually see how the graphene layers get bigger and sort of swell with our lithium because the lithium goes in and out of the graphite.
So here we have an NMC sample, which is a layered lithium, nickel, manganese, cobalt oxide, which is used as a cathode, like an electrode in the lithium-ion battery. And within this layered atomic structure, the lithium ions are intercalated. So these results tell us where the lithium is intercalated into this particle, because the lithium ions need to diffuse into these particles to be intercalated, and features like the grain boundaries here could hinder the lithium ions from do so and lead to battery degradation.
We hebben vandaag veel gezien en geleerd over elektronenmicroscopen en hun belang in de ontwikkeling van lithium-ionen batterijen. Maar hoe ziet de toekomst ervan uit? Dr. Dennis Ferris is CEO van Dragonfly Energy en neemt ons mee in de volgende stappen. Daarvoor gaan we langs een lithium-ionen batterijenfabrikant in Reno. Dat ligt in Nevada in de Verenigde Staten.
Lithium batteries in general are relatively young technology. I mean, when you compare them to modes of storage that we're used to seeing, like lead-acid batteries. Lithium has been progressing pretty rapidly over the last few decades, but I would say over the last decade it really has changed a number of industries. So there's been a lot of emphasis on higher power batteries, on higher energy density, so you can put in a lot more energy in a small space, you can drive farther in a car, you can have your consumer electronics last a lot longer. I think that's been the primary focus. As the field of lithium-ion batteries has progressed, the field of instrumentation has also progressed, because we've had to make better and better instruments to be able to see the very, very small structures that are critical to the performance of the batteries, not just as you produce them, but over time as they age. And so to be able to compile the data necessary to understand the chemistry and physics of what is happening requires novel instrumentation. There's a number of steps that go into making a lithium-ion cell, none of which are particularly trivial. First of all, you've got the electrodes, and the electrodes themselves are basically a powder film. It's either an anode or a cathode powder film that are very strongly adhered to a foil, to a current collector. So that adhesion is not difficult to achieve, while at the same time you need that adhesion with the perfect uniformity, thickness, and porosity. So to get all those things right on a mass scale obviously is not trivial. Now we've gotten really good at it over the years, but if you want to make improvements to that process, you have to ensure that you maintain the uniformity, the porosity, and the adhesion. Beyond that, you have to assemble the cell in a way that's very uniform. You have to ensure that down to the nanoscale, the structures that are formed even during the first charge are perfect, which means this formation mechanism has to be extremely well tuned, and it has to be done, again, uniformly over a very large number of units, so that when you make a product, you don't have a lot of waste, and you have a lot of cells that are very close to each other in terms of capacity, in terms of performance. So overall, it's a feat of mechanical engineering and of chemistry. It's a beautiful product.